The purpose of Lab 4.1 is to use visual models to show images of the basic number theory, and the tools that we're going to need are our color tiles. So I'll give you a few minutes to get those. The most basic concept that we will begin with is showing the family of counting numbers. So we have 1, 2, 3, 4, 'Alright, now I have it fixed. 1, 2, 3, 4. And like before, when we were setting up our patterns, if we set up a table to show the position and the number of tiles, we have 1 tile in the first position, 2 tiles in the second position, 3 tiles in the third position, 4 tiles in the fourth position, and on. So we can easily see by looking at the table that in the 10th position there would be 10 tiles, and in the nth position there would be n tiles. And I can use our prediction to show what would happen in the 100th tile. If I had 100 tiles, I know that's the 100th position. And if I have the 100th position, I know that I have 100 tiles. So I can use my conjecture to go from the position to the tiles, or from the tiles to the position. Now, if I take from this group of counting numbers only the evens, then I begin to see a pattern that is involved with the even numbers. So I have 2, I have 4, I have 6, and with just those 3, sorry, I can see a pattern in the shape that the even numbers are creating. So if I take the position and the number of tiles, I know that in the first position there are 2 tiles, in the second position there are 4, in the third position there are 6, in the fourth position there are 8. And by looking at the relationship, like in the previous chapter, we know that if I have the 10th position, there would be 20 tiles, because the conjecture is the position must be doubled to get the number of tiles. So how I can use that is, if I know the 100th position, I can double it to get the number of tiles. But let's say that I know the number of tiles is 50. Then I will take half of that to get the position. So knowing the number of tiles gives me the position. Giving the position, I can get the number of tiles. Now let's look at the other numbers that were involved in the family of counting numbers. So I have the odd numbers that are left. So if I take the position and the number of tiles, the first position, 1 tile, the second position, 3 tiles, the third position, 5 tiles, and I know that the next number of tiles will be 7 in the fourth position. Notice that the shape of the tiles is no longer a rectangle. It's one less than a rectangle, except for number 1. So by looking at the pattern that's formed, I can see that if I double the position and take 1 away, then I will get the odd number that goes with that position. So 20 minus 1 is 19. And for any position, I double it and subtract 1. So now, if I know that I have the 80th position, the number that falls there would be 2 times 80 minus 1, or 160 minus 1, or 159. So 159 would be the 80th odd number. But if I know the odd number and I want to know the position, then I can use our conjecture and create an equation. So I can add 1 on both sides and divide by 2. And so you have 40 would be the position of the odd number 79. Now notice how I created the picture of the family of odds. Well, there are other ways of writing that picture, and I want us to explore what it would look like to make the family of odds a different shape. So we have 1, 3, 5. It's 7. Maybe not. One more. So we can create an L. To illustrate the family. And another variation of that would be to bring the L below. So when you have students illustrating the number with the tiles, we have to be able to recognize that different variations of representations are fine. So notice I moved the numbers to the right side where I'd had them on the left, and then we had them on top. We could have had them on the right as well. Now, what I'm going to do with these is scoot this back over so you can see number 1. I'm going to bring number 1 over, and I'm going to make a square. So 1 plus 3 is 4, and 4 creates a square. Here we are beginning to illustrate to students the square numbers. 2 squared, which is 4. Now I'm going to bring 4 over and slide it in here. And I've created another square number that is a 3 by 3 square, and that's 9. Then I bring this 3 by 3 square over, and I've created a 4 by 4 square, which is 16. So we've seen the counting numbers, the evens, the odds, and now introducing the family of square numbers and what they look like. We can also use our color tiles to represent consecutive numbers. So if I have 1, the next consecutive number is 1 more than that, and the next consecutive number is 1 more than that. So if we're representing those algebraically, we have n, which is the first number, n plus 1 is the second number, and n plus 2 would be the third number. If I ask you, is the sum of 3 consecutive odd number or consecutive numbers even or odd, that would be an investigation. And in that investigation, you have to be concerned with whether the first number is even or whether the first number is odd. Because if the first number is odd, you have 1 plus 2 plus 3. You have an odd ending in an odd. And that's going to give you 3 plus 3, which is 6, which is an even number. But what if the first number we started with was even? So I'm going to start out with 2. So the next number would be 3, and the next number would be 4. So I'd have 2 plus 3 plus 4, which is 5 plus 4, which is 9. So the sum of 3 consecutive numbers is sometimes even, and it is sometimes odd. So in writing our conjecture, to answer the question, is the sum of 3 consecutive numbers even or odd, you would have to make the statement that if the first number is even, the sum is odd. And if the first number is odd, the sum is even. So we would have to consider both situations. We can also answer more simple questions like if you add an even to an even, do you get even or odd? So if I add 2 plus 4, can I make a rectangle out of that? If I can make a rectangle, then I know that I get even. If I add an odd to an even, 1 plus 2, can I make a rectangle? And the answer to that is no. So the sum is odd. If I add an odd to an odd, so that's like adding 3 to 5. can I make a rectangle? 3 to 5. So I'm going to begin moving to see if I can create a rectangle, which I can. So an odd added to an odd gives an even result. Also, with our number tiles, we can create factors. So if I start out with 4 tiles and I ask you to list all the factors of 4, I would want you to be able to make as many rectangles as you could with 4. So I would start out by making a 1 by 4. Then I could make a 2 by 2. And then I could make a 4 by 1. If I ask you to list the set of factors of 4, I would want you set uses set braces, and I do not duplicate numbers. So I have a 1 by 4 and a 4 by 1. I list them in the order they occur. So I would have 1 and 4. And 2 by 2, I do not duplicate the numbers. So the set of factors of 4 would be 1, 2, and 4, because that's the rectangles that I can make. All right. If I have the set of factors of 3, so I'm going to write or show 3 as we have shown it previously. And now I want to make all the rectangles that I can make out of 3. So I could make a 1 by 3, and I can make a 3 by 1. So the set of factors for 3 are 1 and 3. Alright, let's look at 6. If I have 6 tiles, I can do a 1 by 6 or a 6 by 1. I can do a 2 by 3 or a 3 by 2. And that's all. So the set of factors of 6 would be 1, 2, 3, and 6. So this is how we can let students discover the set of factors. They discover it by creating the possible rectangles that they could from factors. So what I want you to do in the lab is to use the number 20, and I want you to illustrate how you could list the set of factors for 20, creating the number of possible rectangles. Now you can draw it out if you like, or you can use your tiles and take a picture and attach it in Blackboard, or you can draw it out and mail it to me. Again, your assignment for Lab 4.1 is to illustrate how you can find the set of factors of 20. Now, I want to go on to say to you, let's say that you were asked to show the set of factors of 100. There are going to be a lot of factors, and so remember that factors come in pairs. I'm almost finished. Come on in. Come on in, sweet pea. Factors come in pairs. So if I do not want to draw out all the factors of 100, I start out with 1 and 100. Then I see if 2 goes into 100, and it does 50 times. So there will always be a mate for the number that's given. Then I try to see if 3 will go into 100, and it won't. Then I try to see if 100 can be divided by 4, and it can. And then I try to see if 100 can be divided by 5, which it can. And then 6, then 7, then 8, then 9, and last 10. And 10 times 10 is 100, but do not duplicate the 10. You only write the 10 one time. Alright, you know your assignment to illustrate the set of factors of 20. Not just write them, you have to illustrate them.